Mars doesn't want you there, and it has a million ways to kill you. Radiation that shreds your DNA, dust that shreds your lungs, temperatures that swing 300 degrees, an atmosphere that's basically a vacuum, and we're supposed to build a civilization there? And here is a question. If you could bring only one item to Mars to save your life, what would it be? I will pin the most creative answer. Let me know in the comments. Now let's begin. Mars has captivated our imagination for centuries, from the ancient astronomers who named it after the god of war, to modern dreamers like Elon Musk who envision cities beneath its crimson sky. We've been drawn to this planet like moths to a flame. But here's something most people don't realize. Every serious planetary scientist knows that Mars will fundamentally harm the first people we send there. They know it with crystalline certainty, and we're going anyway. This isn't pessimism, this is science, and the story it tells is both magnificent and terrifying. Picture this, you're selected for the first crewed mission to Mars. The training is brutal, but you make it through. Launch day arrives, cameras flash. The world watches as you and your crew lift off from Earth aboard a spacecraft that represents the pinnacle of human engineering. The journey takes approximately 7 months, depending on the orbital alignment of Earth and Mars. During those months, you float in microgravity, watching Earth shrink to a pale blue dot behind you while Mars grows larger ahead. But something is happening to your body. Something invisible, something relentless. You can't feel it, but cosmic rays are piercing through the spacecraft's hull like it's made of tissue paper. These aren't ordinary particles. Galactic cosmic rays, high-energy remnants from exploded stars billions of light years away, slam into your cells at nearly the speed of light. They shred DNA strands, they damage mitochondria, they leave tracks of destruction at the molecular level. According to research published in 2025 analyzing data from NASA's Mars missions, astronauts on a round-trip journey to Mars face radiation exposure approximately 300 times higher than what you experience on Earth's surface. Think about that for a moment. Every single day in space, you're absorbing radiation equivalent to getting dozens of chest X-rays. And it doesn't stop when you sleep, it doesn't stop when you hide. There is nowhere to hide. The spacecraft provides some shielding, of course. But here's the brutal truth. Effective radiation shielding requires either enormous amounts of heavy material, think meters of water or lead, or a magnetic field similar to Earth's. We have neither. The spacecraft walls might stop some of the lower energy particles, but the truly dangerous ones, the iron nuclei, the heavy ions traveling at relativistic speeds, punch straight through. NASA's Human Research Program has spent decades studying this problem. Their latest findings, presented to the NASA Advisory Council in 2024, paint a sobering picture. The radiation exposure during a Mars mission doesn't just increase your cancer risk, though it certainly does that. Models suggest a mortality risk from radiation-induced cancer ranging from 5 to 20% over your remaining lifetime. But cancer is actually one of the more predictable outcomes. Radiation also damages your cardiovascular system. Studies of astronauts who traveled to the moon during the Apollo program showed significantly higher rates of cardiovascular disease decades later compared to astronauts who stayed in low Earth orbit. Mars missions will deliver far higher doses over much longer periods. Your heart, your blood vessels, your circulatory system, all of it takes hits at the cellular level that accumulate over time. And then there's your brain. Recent research has shown that cosmic rays can damage neurons and create neuroinflammation. In animal studies, mice exposed to radiation levels similar to what you'd experience on a Mars mission showed cognitive deficits, memory problems, and anxiety-like behavior months after exposure. The particles literally create lesions in brain tissue. They disrupt the blood-brain barrier, they interfere with the communication between neurons. Imagine returning from Mars with your memory compromised, your ability to focus diminished, your personality subtly but permanently altered. You'd still be you, but not quite the same you who left. Now here's where it gets even more interesting. And by interesting, I mean deeply unsettling. Recent research from ESA's ExoMars Trace Gas Orbiter, published in March of 2026, revealed a counterintuitive finding. Traveling to Mars during solar maximum, when the sun is most active, might actually be safer than traveling during solar minimum. This sounds backwards, right? You'd think more solar activity means more radiation danger. But here's the fascinating physics at play. When the sun is highly active, it generates a stronger solar wind, a stream of charged particles flowing outward from the sun. This solar wind actually sweeps away some of the galactic cosmic rays, acting like a protective bubble around the inner solar system. During solar minimum, when the sun is quiet, that protective effect weakens, and more cosmic rays reach you. Subscribe to this channel and hit that thumbs up button if you're finding this fascinating. The universe has so many counterintuitive surprises, and we're just getting started. Solar flares and coronal mass ejections can unleash devastating bursts of radiation in minutes. These solar proton events are less predictable and potentially more immediately dangerous than the steady drizzle of cosmic rays. During a solar storm, radiation levels can spike to lethal doses within hours. If you're on a spacecraft when a major solar storm hits, you'd need to retreat to a specially shielded storm shelter, a small compartment with extra protection. You'd huddle there, hoping the storm passes before your supplies run out, knowing that if the eruption is powerful enough, even that shelter might not be sufficient. Scientists estimate that a major solar proton event could deliver radiation doses high enough to cause acute radiation sickness, nausea, vomiting, damage to your immune system, and in extreme cases, death within days or weeks. NASA's radiation protection strategy acknowledges this threat but admits that current technology can only partially mitigate it. The rest comes down to timing, luck, and accepting risk. But let's say you survive the journey. Let's say you make it to Mars without a major solar storm, without catastrophic equipment failure, without any of the 1,000 things that could go wrong. 7 months after leaving Earth, you finally descend through the thin Martian atmosphere, and your lander touches down on the surface. Congratulations! You've just arrived at one of the most hostile environments in our solar system. Mars looks beautiful in the photographs: sweeping dunes, towering volcanoes, ancient river valleys carved into rust-colored rock. Olympus Mons rises nearly 25 kilometers into the sky, 3 times the height of Mount Everest. Valles Marineris stretches across 4,000 kilometers, dwarfing the Grand Canyon. The landscape is alien and sublime, a testament to billions of years of geological history. But step outside without a spacesuit, and you'd be dead in about 90 seconds. The atmosphere of Mars is less than 1% as thick as Earth's. There's essentially no air pressure. Your blood would literally boil at body temperature, a process called ebulism. The water in your soft tissues would vaporize. You'd lose consciousness within 15 seconds as oxygen stopped reaching your brain. And even if someone could somehow revive you after that, the damage would be catastrophic and irreversible. So you live in a spacesuit or a pressurized habitat, always. Every single moment of every single day. Want to step outside to collect a soil sample? Suit up. Want to repair a solar panel? Suit up. Want to explore that interesting rock formation a kilometer away? Suit up. The suits themselves are engineering marvels, but they're also exhausting to use. Current spacesuit designs require significant physical effort to move around. The suit resists your movements. Your hands get tired from operating the gloves. After a few hours of work outside, you're physically drained. And you have to do this day after day for months or years, depending on how long the mission lasts. The habitats offer protection, but they're essentially sealed cans. You're breathing recycled air, drinking recycled water, eating food that's either freeze-dried or grown in small hydroponic systems. there are no fresh vegetables unless you grow them yourself. There's no rain, no wind on your face, no walks in a forest, no spontaneous trips to the ocean. There's Mars, and there's your habitat, and there's the work you came to do. Psychological studies of people in isolated environments, Antarctic research stations, submarine crews, simulated Mars habitats on Earth consistently show the same patterns. People adapt, but they also struggle. Conflicts arise over trivial things. Sleeping patterns get disrupted. Some people become withdrawn. Others become irritable. The combination of confinement, monotony, danger, and distance from Earth creates unique psychological stressors that no amount of training fully prepares you for. And you can't just leave. You can't say, "I've had enough, I'm going home." The orbital mechanics that brought you to Mars only allow return windows approximately every 26 months when Earth and Mars align properly. If you arrive at Mars and discover you can't handle it, psychologically, medically, or otherwise, you're stuck for years. Let me paint you a picture of what a day on Mars might actually look like. You wake up in your sleep pod, a compartment roughly the size of a closet. The habitat's lighting system simulates a Martian dawn, gradually increasing in brightness to help maintain your circadian rhythm. But it's artificial. Everything here is artificial. You check the habitat's environmental systems on a tablet. Oxygen levels, nominal. Carbon dioxide scrubbers, functioning. Water recyclers, operating at 93% efficiency. That last number concerns you slightly. If the water recycling system drops below 80%, you'll start losing precious water faster than the system can recover it from the atmosphere, from your sweat, from your exhaled breath, from your urine. Water on Mars is theoretically abundant, frozen beneath the surface, locked in the polar ice caps, but extracting it requires energy and equipment, both of which are limited. You float out of your sleep pod. Wait, not float, walk. Sort of. Here's something that doesn't get emphasized enough in the glossy mission presentations. Mars has only 38% of Earth's gravity. That might sound liberating at first. You can jump higher, lift heavier objects, move with less effort. But your body doesn't experience it as freedom. Your body experiences it as a continuous, unrelenting assault on your musculoskeletal system. Research published in Sports Medicine in 2021 analyzed data from astronauts who spent long periods in microgravity and created projections for Mars missions. The findings were stark. Even with aggressive exercise countermeasures, 2 to 3 hours of resistance training every single day, astronauts lose significant bone density and muscle mass. In microgravity, astronauts can lose up to 1 to 2% of their bone mass per month in weight-bearing bones like the spine, pelvis, and legs. On Mars, with its partial gravity, the loss rate is lower but still substantial. Models predict that after a 3-year mission, astronauts could lose 12 to 15% of their bone density in critical areas. To put that in perspective, the World Health Organization defines osteopenia, the precursor to osteoporosis, as bone density that's 1 to 2.5 standard deviations below the young adult mean. After a Mars mission, you'd likely meet that criteria. Some models predict that 100% of astronauts on a long-duration Mars mission would develop osteopenia, with 33% at risk for full osteoporosis. Your bones aren't just getting weaker. They're fundamentally changing structure. The trabecular bone, the spongy inner layer that provides strength, deteriorates. The bone remodeling process, where old bone is broken down and new bone is formed, gets disrupted. Bone resorption accelerates while bone formation lags behind. Your skeleton is literally eating itself, and there's only so much exercise can do to slow the process. But wait, there's more. And it gets worse. Your muscles atrophy. Without Earth's gravity constantly pulling on them, your postural muscles, the ones that keep you upright, that support your spine, that maintain your posture, start to waste away. Your heart, which is essentially a muscle, doesn't have to work as hard to pump blood upward against gravity. It gets smaller, your cardiovascular capacity diminishes. Studies from the International Space Station show that even with extensive exercise regimens, astronauts experience measurable declines in muscle mass, strength, and endurance. When they return to Earth after 6 months, many need assistance walking. Some take weeks or months to fully recover. And that's after 6 months in microgravity, with the knowledge that they're coming home to Earth's full gravity and immediate medical care. You'll be on Mars for potentially 2 to 3 years. And when you return, you'll face 7 more months of microgravity during the journey back. By the time you reach Earth, your bones might be so brittle that the landing forces could cause fractures. Your muscles might be so atrophied that you can't stand. Your heart might struggle to pump blood effectively against Earth's gravity. A study published in PLOS One in 2020 analyzed femoral neck bone density data from 69 astronauts and created models for Mars missions. The predictions were grim. 62% of astronauts on a 400 to 600-day opposition-class mission would develop osteopenia, with 33% at risk for osteoporosis. For conjunction-class missions lasting 1,000 to 1,200 days, 100% would develop osteopenia. 100%. This isn't speculation. This is based on actual data from astronauts, projected forward using established mathematical models of bone loss in reduced gravity environments. Now you might be thinking, okay, bone loss is serious, but surely we can develop better countermeasures, right? Better exercise equipment, pharmaceutical interventions, maybe something we haven't thought of yet? Maybe. Research continues. Scientists are exploring various approaches: bisphosphonate drugs that slow bone resorption, high-impact exercises that stimulate bone formation, electrical stimulation of muscles, artificial gravity created by rotating spacecraft. But here's the sobering reality. We've been sending astronauts to space for over 60 years, and we still haven't solved the bone loss problem, not even close. The best we've achieved is slowing it down. So every morning on Mars, you spend the first 2 to 3 hours exercising, not because you want to, not because it's enjoyable, but because if you don't, your body will deteriorate even faster. You strap into the resistance exercise machine and go through your prescribed routine. Squats, deadlifts, rows, presses, all carefully designed to load your bones and muscles in ways that partially simulate Earth's gravity. It's exhausting work, and you do it knowing it's only partially effective, knowing that you're still losing bone density, still getting weaker, still compromising your long-term health. After your workout, you eat breakfast. The food is nutritionally complete, but monotonous. You've eaten these same meals dozens of times already, and you'll eat them hundreds more times before you leave. Fresh food is a rare luxury, only available when the small hydroponic garden produces something edible. Everything else comes from packages shipped from Earth at enormous cost. Then it's time for your daily health check. You measure your blood pressure, heart rate, oxygen saturation, body temperature. You collect biological samples, blood, urine, saliva, for analysis. The Habitat's medical diagnostic system runs tests to monitor bone density markers, muscle breakdown indicators, radiation exposure biomarkers, immune system function, and dozens of other parameters. This isn't optional. Mission protocols require daily health monitoring because out here, a medical emergency can become fatal long before help arrives. Speaking of medical emergencies, let's talk about something that keeps mission planners awake at night. What happens if someone gets seriously sick or injured on Mars? If you enjoyed learning about the hidden dangers of Mars so far, you should definitely check out my other video called Why the First Humans on Mars Will Never Come Back. It goes even deeper into the one-way aspects of this journey and explores why some scientists believe the first Mars colonists might not have a choice about returning. The link is in the description, and I think you'll find it absolutely eye-opening. But back to medical emergencies. On Earth, if you have a heart attack, appendicitis, or a severe injury, you can reach advanced medical care within hours. On Mars, the nearest hospital is at least 7 months away. The speed of light creates a communication delay of anywhere from 4 to 24 minutes one way, depending on where Earth and Mars are in their orbits. You can't have a real-time conversation with Earth. You can't consult with a doctor in the moment. You send a message, wait, receive a response, wait again. The habitat includes medical supplies and equipment, of course, but it's limited. You can handle minor injuries, common illnesses, routine procedures. But what if someone develops appendicitis and needs emergency surgery? What if someone has an aneurysm? What if someone breaks a bone, which becomes more likely as bone density decreases? NASA has run simulations and training programs for astronaut medical emergencies. One astronaut typically receives extensive medical training to serve as the crew medical officer. But let's be honest, would you want a geologist with a few hundred hours of medical training performing emergency surgery on you with equipment designed for zero-gravity use in a Mars habitat with no backup, no anesthesiologist, no surgical team, and a 20-minute communication delay to consult with Earth? The answer is obvious, but it might be your only option. And then there's the psychological dimension, which might be the most unpredictable variable of all. Imagine being further from home than any human has ever been. Earth is a point of light in the sky, indistinguishable from other bright stars without a telescope. Everyone you've ever known, every place you've ever been, every comfort and familiarity, all of it exists on that distant, unreachable point of light. Your family can't visit. You can't call them on the phone. You can send video messages, but there's that delay, minutes or tens of minutes depending on orbital positions. Conversations become asynchronous exchanges, not real interactions. Psychological studies of Antarctic winter overcrews, submarine personnel, and participants in Mars simulation habitats like HICs have documented the phenomenon called third quarter syndrome. About 2/3 of the way through a long-duration, isolated mission, people tend to experience increased irritability, depression, conflicts with crew members, and decreased motivation. The novelty has worn off. The end still seems far away. The monotony becomes oppressive. Now multiply that by the fact that you're not in Antarctica, where rescue is theoretically possible, but on Mars, where it absolutely isn't. You can't leave. You can't be evacuated. If things go wrong with the crew dynamics, you still have to live and work together in close quarters for potentially years. Space agencies screen candidates extensively for psychological resilience. They select people who work well in teams, who handle stress effectively, who remain calm under pressure, but even the best selected crews have limits. In confined, isolated, dangerous environments, small annoyances become major frustrations. Someone's habits, the way they chew, the way they leave equipment out, the way they breathe, can become sources of intense irritation when you're forced to be around them constantly. Conflicts are inevitable. The question is whether they can be managed or whether they escalate into mission-threatening problems. History provides cautionary examples. The Soviet Salyut and Mir space stations experienced crew conflicts significant enough to affect mission objectives. On Mars, with no possibility of crew rotation, no ability to send someone home early, and limited space to get away from each other, such conflicts could become genuinely dangerous. And beneath all of this, the radiation, the bone loss, the isolation, the confinement, runs another current of danger that most people don't even know about. The soil itself is trying to kill you. The Martian soil looks harmless in photographs, rusty red, fine-grained, almost powder-like in some regions. You might imagine running your gloved fingers through it, examining it for signs of ancient microbial life, analyzing its mineral composition, and you will do these things. But you need to understand something crucial. Martian soil isn't just dirt. It's a chemical weapon that's been waiting 4 billion years for something to contaminate. In 2007, NASA's Phoenix lander discovered something unexpected in the Martian regolith: perchlorates. These are chemical compounds containing chlorine and oxygen, and they're everywhere on Mars. Not just in trace amounts, we're talking about concentrations of roughly 0.5 to 1% of the soil by weight. To put that in perspective, that's about 10,000 times higher than typical perchlorate concentrations found in Earth's soil. Why does this matter? Because perchlorates are toxic to humans. They interfere with thyroid function by blocking iodine uptake, which can lead to hypothyroidism, metabolic disorders, and developmental problems. They're reactive oxidizers, which means they can trigger harmful chemical reactions in biological systems. They're particularly dangerous to developing fetuses and children, which has profound implications for any long-term colonization plans. And here's the kicker: they're hygroscopic, meaning they absorb moisture from the air. In Mars' extremely low humidity environment, perchlorate salts can create tiny pockets of liquid brine by pulling water vapor from the atmosphere, which sounds useful until you realize you might accidentally create toxic solutions that can penetrate equipment or habitat seals. Research published in January 2026 revealed something even more unsettling. Mars is actively manufacturing these perchlorates. Scientists discovered that electrostatic discharges, essentially lightning-like phenomena in dust storms, can create perchlorate compounds from chlorine and oxygen in the atmosphere. This means Mars has a natural perchlorate factory that's been running for billions of years, continuously producing and distributing these chemicals across the planet's surface. When you walk on Mars, perchlorate dust will get everywhere. It'll cling to your spacesuit with electrostatic attraction. It'll accumulate in the airlock. Tiny particles will inevitably make their way into the habitat despite filtration systems. You'll breathe trace amounts. It'll contaminate your food production systems. Your water recycling equipment will need perchlorate removal systems that add weight, complexity, and failure points to mission-critical infrastructure. Studies on how perchlorates affect microorganisms show mixed results. Research published in February 2026 in Solar System Research found that perchlorate has an inhibitory effect on Bacillus subtilis bacteria under moisture-scarce conditions very similar to Mars. However, another study published in April 2026 found that yeast cells could survive perchlorate exposure under Mars-like conditions by forming protective molecular clusters. This variability makes it difficult to predict exactly how Earth life, including crops you'd try to grow, would respond to perchlorate-contaminated Martian soil. You can't just use Martian soil for agriculture without extensive treatment. You'd need to wash it repeatedly to remove perchlorates, which requires enormous amounts of water you don't have in abundance. You'd need to add nutrients that Martian soil lacks. You'd need to introduce beneficial microorganisms. Essentially, you'd need to create Earth soil on Mars, an energy-intensive and resource-demanding process that must work reliably or you don't eat. And perchlorates are just the beginning of the soil chemistry problems. Martian regolith contains iron oxides, hence the red color, but also potentially toxic heavy metals, sulfates, and other compounds that could pose health risks with prolonged exposure. The dust particles themselves are incredibly fine, much finer than most Earth dust, with sharp, angular edges because Mars lacks the water and wind patterns that round particles on Earth. When inhaled, these particles could cause serious respiratory problems, similar to silicosis in miners, or the lung problems experienced by Apollo astronauts exposed to lunar dust. Speaking of dust, let's talk about Martian dust storms. One of the few aspects of Mars that science fiction actually gets somewhat right, though often exaggerated. Mars is famous for its dust storms. Every Martian year, which lasts 687 Earth days, regional dust storms develop. These can cover continent-sized areas and last for weeks. Approximately every 3 Mars years, which equals about 5.5 Earth years, conditions align to create planet-encircling global dust storms that can last for months and obscure the entire planet's surface. The movie The Martian depicted a dust storm so powerful it could knock over equipment and threaten astronauts. That part is actually exaggerated. Mars' atmosphere is so thin that even a 100 km/h wind would feel more like a gentle breeze on Earth. The atmospheric pressure is too low to generate the kind of mechanical force shown in the film. A Martian dust storm won't blow you away, but it will kill you in other ways. The real danger of dust storms isn't the wind, it's what the dust does to your life support systems. Solar panels get covered in fine dust, dramatically reducing power generation. NASA's Opportunity rover, which operated on Mars for 15 years, finally succumbed to a global dust storm in 2018 when its solar panels became too obscured to charge its batteries. The rover went into hibernation mode and never woke up. If you're relying on solar power, which most early Mars missions will be, a major dust storm means your power generation drops dramatically. 70% reduction, 80%, 90%. Your habitat starts running on battery reserves. You shut down non-essential systems to conserve power. Heating becomes a luxury you carefully ration. Water recycling slows down. Food production in the hydroponics bay halts because there's not enough power for the grow lights. And the storm continues. Days become weeks, weeks become months. You're making impossible calculations. How long will the batteries last? Can we reduce power consumption enough to outlast the storm? What do we shut down next? At what point do we acknowledge that we're going to die here, 70 million kilometers from home, suffocating in the dark as our oxygen scrubbers fail and carbon dioxide slowly accumulates in the habitat? Recent research published in February 2026 discovered a new danger associated with dust storms. Scientists analyzing data from multiple Mars orbiters found that an unusually intense, localized dust storm in August of 2023 drove massive vertical transport of water vapor during the northern summer season. Within days of the storm, enhanced water vapor concentrations appeared at altitudes over 40 kilometers across northern high latitudes, followed by an increase in escaping hydrogen detected at the exobase, the upper boundary of Mars' atmosphere, where gases can escape to space. This matters because it reveals a mechanism for how Mars continues losing water. The planet was once much wetter. We have overwhelming geological evidence of ancient rivers, lakes, possibly even an ocean covering much of the northern hemisphere. Where did that water go? Some froze underground. Some is locked in the polar ice caps. But much of it was lost to space through processes like this. Dust storms heat the atmosphere, allowing water vapor to reach high altitudes where ultraviolet radiation breaks it down into hydrogen and oxygen, and the hydrogen escapes into space. For a Mars colony, this has implications beyond historical curiosity. It means that any water you extract from Martian ice and introduce into the habitat or use for agriculture could, through various pathways, eventually contribute to atmospheric water vapor that escapes during dust storms. You're not just managing a closed water cycle within your habitat, you're potentially losing water to space over time, adding another layer to the resource management nightmare. But let's step back from the technical dangers for a moment and contemplate something more profound and more unsettling: what Mars does to your perception of reality itself. Earth has protected life for billions of years with its magnetic field. its thick atmosphere, its abundant water, its stable climate. These aren't luxuries, they're the baseline conditions that shaped every aspect of how your body and brain function. Your circadian rhythm evolved under a 24-hour day-night cycle, lit by a sun at a specific brightness and color temperature. Your respiratory system evolved breathing air at sea-level pressure with 21% oxygen. Your inner ear's balance system evolved under one standard Earth gravity. Your bones, muscles, cardiovascular system, everything about you is optimized for Earth conditions. Mars violates all of these baseline conditions simultaneously. The Martian day, called a sol, is 24 hours and 39 minutes long, close to Earth's day, but not quite. That 39-minute difference doesn't sound like much, but your circadian rhythm is precisely tuned. Studies of people trying to adapt to Mars-like day lengths show disrupted sleep patterns, decreased cognitive performance, and increased errors. Your body never quite settles into the rhythm. You're perpetually jet-lagged. The Sun appears about 2/3 the size in the Martian sky because Mars orbits further from the Sun. Solar illumination at Mars's surface is about 43% of what you'd experience on Earth. Even on a clear day with no dust storms, it would feel like perpetual late-afternoon twilight. This affects your mood, your vitamin D production, your psychological well-being. Seasonal affective disorder is a recognized condition on Earth caused by reduced sunlight exposure. On Mars, you'd live in permanent, reduced sunlight. The sky itself is the wrong color. On Earth, you look up and see blue because our atmosphere scatters blue light. On Mars, the thin atmosphere filled with fine dust particles scatters red light, creating a butterscotch or pinkish sky during the day. Near sunset, it's reversed. You'd see blue halos around the sun while the rest of the sky glows red. It's beautiful in an alien way, but it's also a constant reminder that you're not home, that you're living somewhere fundamentally not designed for human existence. And then there's the silence. Mars has no substantial atmosphere to carry sound effectively. Wind makes almost no noise. There are no birds, no insects, no rustling leaves, no distant traffic, no human activity, except what your small crew creates. The soundscape is eerily quiet except for the mechanical hum of habitat systems, the hiss of air recyclers, the occasional creak of equipment responding to temperature changes. Humans evolved in rich acoustic environments. We're constantly processing ambient sounds, using them to build our sense of place and safety. Remove that ambient soundscape and something feels wrong at a deep, primal level. Studies in artificially silent environments show that people become uncomfortable after extended periods. They report feeling disoriented, anxious, hyper-aware of bodily sounds like their heartbeat and breathing. On Mars, you'd live in a mostly silent world punctuated by mechanical sounds, never hearing the complex natural acoustic environment your brain expects. All of these factors, the altered gravity, the wrong sun, the strange sky, the silence, the confinement, the danger, combine to create a profoundly disorienting experience. Psychologists call this environmental mismatch stress. Your brain receives thousands of signals that say, this is not where you should be. And unlike temporary stress, which people can endure knowing it will end, this is indefinite stress. You can't escape it. It's your new reality for years. Some people might adapt relatively well. Others might develop serious psychological problems, anxiety disorders, depression, dissociative symptoms. The isolation and danger compound these effects. And here's the terrifying part. You won't know how you'll really respond until you're actually there, and by then, you're committed. Now let's talk about something that might be the most insidious danger of all, the slow, invisible degradation of your cognitive abilities. You came to Mars as a highly trained scientist, engineer, or astronaut. Your mind is sharp. You've solved complex problems, made split-second decisions, demonstrated exceptional mental capacity. That's why you were selected, but Mars doesn't care about your credentials. It's going to diminish you, and you might not even notice it happening. The radiation exposure we discussed earlier doesn't just increase cancer risk, it actively damages your brain structure and function. Studies conducted at NASA's Space Radiation Laboratory at Brookhaven National Laboratory exposed rodents to radiation environments simulating deep space and Mars missions. The results were deeply concerning. Animals showed significant cognitive deficits months after exposure, impaired memory formation, reduced problem-solving abilities, anxiety-like behaviors, and measurable changes in brain structure. The mechanism is straightforward and brutal. High-energy cosmic ray particles tear through neurons like bullets through tissue. They create tracks of ionization damage. They trigger inflammatory responses that can persist for months or years. They damage the hippocampus, the brain region crucial for forming new memories. They alter neurotransmitter systems. They disrupt the delicate balance of neural networks that enable higher cognitive functions. In human terms, this means you might start having trouble remembering recent events. You might find complex problem-solving more difficult than it used to be. Your reaction time might slow. You might experience mood changes, increased anxiety, irritability, or depression that have a physiological basis in radiation-induced brain damage, not just psychological stress. And here's the cruel irony. These cognitive deficits occur precisely when you most need your mental faculties to be at peak performance. You're operating complex machinery in an environment where mistakes can be fatal. You're making critical decisions about resource allocation, equipment repair, mission planning. You need to be sharp, but your brain is being degraded by invisible particles you can't avoid. The situation gets worse when you consider the cumulative effects of multiple stressors. Sleep deprivation, which is likely given the disrupted circadian rhythms and high-stress environment, impairs cognitive function. Chronic stress elevates cortisol levels, which damages the hippocampus over time. Isolation and monotony reduce cognitive stimulation. Nutritional deficiencies, difficult to avoid with a limited diet, affect brain function. Physical deconditioning reduces cerebral blood flow. All of these factors work synergistically. The whole becomes greater than the sum of parts. You're not just dealing with one problem, you're dealing with a cascade of interconnected problems, each making the others worse. Mission planners know this. Psychological support protocols include regular cognitive assessments, mental health check-ins, prescribed social activities, and communication with Earth-based psychologists. But these are band-aids on a compound fracture. The fundamental problem, that Mars is inherently hostile to human cognition, remains unsolved. And let's be brutally honest about what happens if someone's cognitive function degrades significantly during the mission. On Earth, if someone develops dementia, traumatic brain injury, or serious mental illness, they receive specialized care in dedicated facilities with professional staff. On Mars, your options are extremely limited. The crew medical officer has some training, but they're not a neurologist, not a psychiatrist, not equipped to handle serious neurological or psychiatric emergencies. What do you do if a crew member develops psychosis, if someone becomes so depressed they're suicidal, if someone's cognitive decline makes them unable to perform essential duties but they refuse to acknowledge it? These aren't hypothetical scenarios, they're possibilities mission planners have war-gamed in simulation exercises. The answers are never satisfying because the constraints are so severe. You can't evacuate someone, you can't bring in specialists. You can sedate someone if absolutely necessary, but then you've lost a crew member's contributions and increased the workload on everyone else. In a small crew, 6 to 8 people is typical for early Mars missions. Losing one person's productivity is catastrophic. Everyone else has to absorb their duties while maintaining their own responsibilities, increasing stress and exhaustion for the entire crew. Now let's shift to something equally disturbing. What happens to your immune system on Mars? Your immune system is extraordinarily complex, involving trillions of cells coordinating to protect you from pathogens, remove damaged cells, and maintain your body's internal balance. It evolved under Earth conditions with Earth gravity. Take that away, and the whole system starts malfunctioning. Research on astronauts in low Earth orbit has consistently shown immune system dysregulation during spaceflight. White blood cell counts change. The distribution of immune cell types shifts. T-cell function becomes impaired. The body's ability to mount effective responses to infections decreases. Latent viruses that your immune system normally keeps suppressed, like herpes, viruses that large percentages of humans carry asymptomatically, can reactivate during spaceflight. Studies have found that astronauts shed significantly more virus particles during and after missions, indicating immune system stress. Some astronauts develop shingles, a painful reactivation of the chickenpox virus, during or shortly after missions. Others experience reactivation of Epstein-Barr virus or cytomegalovirus. On Mars, you'll face this immune suppression for years, not months. And you'll be in an environment where medical treatment options are severely limited. A simple infection that would be easily treated on Earth could become life-threatening. A wound that would heal normally might become infected and difficult to treat with the limited antibiotics available. And here's something that keeps medical researchers awake at night. The microbes that inevitably travel with you to Mars might behave differently in reduced gravity and high radiation environments. Studies on the International Space Station have shown that some bacteria become more virulent in microgravity. They grow faster, form thicker biofilms, develop increased resistance to antibiotics. The enclosed habitat environment creates ideal conditions for microbes to spread among crew members with nowhere to escape. You and your crewmates are essentially living in a sealed container, recycling the same air, touching the same surfaces, sharing the same spaces. Any pathogen one person introduces or develops will spread to everyone. On Earth, you go outside, you interact with new people, you're exposed to a diverse microbial environment that actually helps maintain healthy immune function through constant stimulation. On Mars, your microbial environment becomes increasingly homogeneous, just you, your crewmates, and the microbes you brought with you. This has profound implications. The human microbiome, the trillions of microorganisms living in and on your body, plays crucial roles in digestion, immune function, even mood regulation through the gut-brain axis. In the closed Mars habitat environment, everyone's microbiomes will start converging, becoming more similar to each other. The diversity that helps maintain health decreases. This could lead to dysbiosis, microbial imbalances that contribute to various health problems, and we haven't even discussed dental problems. Imagine developing a serious cavity, an abscess, or needing a root canal on Mars. The crew medical officer has basic dental supplies, but they're not a dentist. Performing complex dental procedures without proper equipment, training, or anesthesia options would be excruciating for the patient and traumatic for everyone involved. Yet dental problems are common, and they won't stop happening just because you're on Mars. Let me tell you about something else that doesn't make it into the inspiring Mars mission videos. What happens to your eyes? Astronauts on the International Space Station have experienced a condition called spaceflight-associated neuroocular syndrome, or SINS. The mechanism isn't fully understood, but it appears related to fluid shifts in the body caused by microgravity or reduced gravity. Without gravity pulling fluids downward, more fluid accumulates in the upper body and head. This creates increased intracranial pressure, literally pressure inside your skull. This pressure can flatten the back of the eyeball, cause optic disc swelling, create cotton wool spots on the retina and lead to vision changes. Some astronauts have experienced significant vision degradation during missions, a serious problem when you need clear vision to operate complex equipment, read displays, perform delicate repairs, and navigate hazardous terrain. On Mars, with its partial gravity, the effects might be less severe than in complete microgravity, but they're still likely to occur. And if your vision degrades significantly, what are your options? The habitat doesn't have an ophthalmology clinic. You can't get prescription glasses easily adjusted. If the vision problems become severe enough, you might lose the ability to perform critical mission tasks. The cumulative picture of physiological degradation is staggering. Your bones weaken. Your muscles atrophy. Your cardiovascular system deconditions. Your brain accumulates radiation damage. Your immune system becomes suppressed. Your vision potentially degrades. Your cognitive function declines. And all of this happens simultaneously, each system's decline affecting the others in a cascade of deterioration. You're becoming a different person, a frailer, weaker, more vulnerable version of yourself. And this transformation is happening because you're pursuing one of humanity's grandest ambitions. There's something profoundly tragic about that. Now let's discuss the return journey, because in some ways, it's even more dangerous than the trip to Mars. When you finally leave Mars after spending months or years on the surface, you're not the same person who arrived. You've lost significant bone density. Your muscles have atrophied despite rigorous exercise. Your cardiovascular system has adapted to lower gravity. Your body has fundamentally changed. Then you climb into a spacecraft and spend another 7 months in microgravity for the return to Earth. This compounds all the problems. The bone loss that slowed on Mars' partial gravity accelerates again in zero gravity. The muscle atrophy worsens. Your heart, already deconditioned, weakens further. Studies of astronauts returning from 6-month stays on the International Space Station show significant recovery challenges. Many can't walk unassisted immediately after landing. Some take weeks to regain full mobility. Their bone density slowly recovers, but it can take months or years, and some astronauts never fully return to their pre-flight baseline, especially in trabecular bone. After a Mars mission, you'll have spent perhaps 7 months in zero gravity going to Mars, potentially 18 months on Mars in partial gravity, and another 7 months in zero gravity returning. That's over 2.5 years of bone loss, muscle atrophy, cardiovascular deconditioning, and radiation exposure. When you finally re-enter Earth's atmosphere and experience the deceleration forces of landing, your weakened body will be subjected to multiple G-forces, potentially 3 to 5 times Earth's gravity for brief periods. Your brittle bones might fracture under these loads. Your weakened heart might struggle to pump blood effectively. You might lose consciousness. And if you survive the landing intact, you'll face months of grueling rehabilitation. Physical therapy to rebuild muscles. Weight-bearing exercises to stimulate bone regrowth. Cardiovascular conditioning to restore heart function. You'll probably need assistance with basic activities initially. Walking, standing, even sitting upright might be difficult. Some of the damage might be permanent. Studies suggest that extensive bone loss might not fully reverse, especially in older astronauts. Radiation-induced cellular damage persists. Cognitive effects from radiation might be irreversible. You might return to Earth with chronic pain, mobility limitations, increased cancer risk, cognitive deficits, and various other health problems that will affect you for the rest of your life. This is the price. This is what Mars demands. And we haven't even touched on reproduction. What if someone becomes pregnant on Mars, either intentionally or accidentally? The radiation exposure alone would pose enormous risks to fetal development. The reduced gravity could affect how a fetus develops its skeletal and muscular systems. The nutritional limitations, the stress, the confined environment, all of it would create conditions far from optimal for pregnancy. No human has ever gestated or been born in reduced gravity. We have no idea what long-term effects this might have. Animal studies in microgravity have shown various developmental problems, but these are limited and don't fully translate to human pregnancies. Would a child born on Mars be able to adapt to Earth's gravity if they ever visited? Would their bones and muscles develop properly? We simply don't know. For any serious long-term colonization effort, these questions become critical. If humans can't successfully reproduce and raise healthy children on Mars, then colonization in the traditional sense becomes impossible. You'd have a research outpost, not a colony, a place people visit for limited periods before returning to Earth, assuming they survive the journey back. Let's talk about something that might seem mundane, but is actually one of the most critical and terrifying aspects of Mars colonization: producing your own food. On Earth, agriculture seems straightforward because we're surrounded by the infrastructure that makes it possible. You have soil enriched by billions of years of biological activity. You have reliable rainfall or irrigation systems connected to vast water resources. You have pollinators, bees, butterflies, other insects. You have a stable climate with predictable seasons. You have an atmosphere that filters harmful radiation while letting visible light through. You have a diverse ecosystem of microorganisms that cycle nutrients and maintain soil health. Mars has none of this. The initial missions will bring food from Earth, freeze-dried meals, nutritionally complete but monotonous and limited by payload weight. A single kilogram of supplies costs somewhere between $5,000 to $20,000 to transport to Mars, depending on mission architecture and technology. Sending enough food for a crew of 6 people for 2 years means launching tens of thousands of kilograms, at a cost reaching into the hundreds of millions of dollars just for the food. This isn't sustainable. Any long-term presence on Mars requires growing food locally, which means you need to create a functioning agricultural system in one of the most hostile environments imaginable. Let's start with the soil problem we touched on earlier. Martian regolith contains perchlorates that must be removed. It lacks organic matter, no decomposed plant material, no humus, none of the biological components that make Earth soil alive. It has unfavorable pH levels for most plants. The nutrient ratios are completely wrong. To create usable growing medium, you'd need to wash the regolith extensively to remove perchlorates, which requires precious water. Then you'd need to add nutrients, nitrogen, phosphorus, potassium, and various micronutrients that plants require. Where do these come from? Initially, they'd be brought from Earth, adding more mass and cost. Eventually, you'd need to establish nutrient cycling systems using composted human waste, food scraps, and dead plant material. Yes, we're talking about carefully managing human feces as a critical agricultural resource. The sanitation practices we take for granted on Earth, flush and forget, don't work on Mars. Every biological output from your body becomes a potential input for food production. You'll become intimately familiar with composting toilets, waste processing systems, and the chemistry of turning human excrement into fertilizer. Research published in PLOS One examined whether plants could grow in Mars simulant soil. Scientists used soil mixtures designed to match Martian regolith chemistry and tested various plant species. Some plants could germinate and grow in treated Mars simulant, but they required extensive soil amendments, careful water management, and controlled environments. The yields were lower than Earth-grown equivalents, and the plants often showed stress symptoms. A study published in Open Agriculture in March 2026 tested 14 plant species in Mars regolith simulant. The researchers found that most species showed poor germination and growth compared to controls in Earth soil. Only a few species, certain varieties of cress, rocket, and tomatoes, showed any promise, and even these required significant soil treatment and supplementation. Now let's add the complication of growing these plants inside a pressurized habitat with artificial lighting. Natural sunlight on Mars is only about 43% as intense as Earth sunlight, and during dust storms it drops further. You can't rely on natural light alone for food production. You need artificial grow lights, which means electricity, which means power generation systems that work reliably. LED grow lights are efficient, but they still consume significant power. A medium-sized hydroponic or aeroponic growing system capable of supplementing food for 6 people might require several kilowatts of continuous power. That's on top of life support systems, heating, water recycling, scientific equipment, and all other habitat power demands. The plants need carbon dioxide, which you have plenty of. Humans exhale it, and Mars' atmosphere is 95% carbon dioxide. But they also need careful environmental controls, temperature maintained within specific ranges, humidity controlled to prevent both drought stress and fungal growth, air circulation to prevent CO2 depletion around leaf surfaces, and protection from the extreme temperature swings that occur outside the habitat. Then there's pollination. Many food crops require pollination to produce fruits and seeds. On Earth, insects and wind handle this. On Mars, you'll need to hand-pollinate many plants using small brushes to transfer pollen from flower to flower. This is labor-intensive, time-consuming work that must be done correctly, or the plants won't produce food. Imagine spending hours each week carefully brushing pollen onto tomato flowers while your other responsibilities pile up. The psychological impact of eating a monotonous diet shouldn't be underestimated. Food is deeply connected to culture, comfort, and psychological well-being. Earth's diverse cuisine, the flavors, textures, variety, is something we take for granted. On Mars, you'll eat the same limited selection of crops that can be grown in your habitat, supplemented by packaged foods from Earth that you've already eaten countless times. Studies of isolated crews consistently show that food quality and variety significantly affect morale. In the Mars 500 simulation, where 6 people lived in isolation for 520 days to simulate a Mars mission, food complaints were frequent. The food was nutritionally adequate but monotonous, and participants reported that it negatively affected their psychological well-being. And here's a terrifying scenario. What if your food production system fails? What if a disease sweeps through your crops? What if your grow lights malfunction and you don't have replacement parts? What if contamination introduces perchlorates into your carefully treated growing medium? On Earth, agricultural failure means you buy food from elsewhere. On Mars, it means you slowly starve while waiting 7 months for the next resupply mission, if one is even scheduled. You'd ration the remaining packaged food, cutting calories to extend supplies as long as possible. Chronic hunger would set in. Your body, already stressed by radiation, reduced gravity, and confined living, would begin consuming its own tissues for energy. Physical and cognitive performance would decline further. Conflicts would intensify as stress and hunger made everyone more irritable. Eventually, if resupply didn't arrive in time, the mission would end in tragedy. And the worst part? Earth would watch it happen in real time on delayed video messages, powerless to intervene. This scenario isn't far-fetched. Biological systems are inherently unpredictable. A single pathogen, pest, or equipment failure can cascade into catastrophic crop loss. On Earth, we have redundancy. If one farm fails, others compensate. On Mars, your entire food production system fits inside a small, pressurized greenhouse module. There's no backup, no alternative suppliers, no margin for error. Let's discuss water management, which is inextricably linked to food production. Water is abundant on Mars in the form of ice, both at the polar caps and in subsurface deposits. The Mars Reconnaissance Orbiter and Mars Express missions have mapped extensive subsurface ice deposits at various latitudes. Sounds reassuring, right? Water availability solved? Not quite. Extracting that ice requires drilling or excavating through Martian soil, which means equipment, energy, and time. Then you need to heat the ice to melt it, which requires more energy. The water will be contaminated with Martian soil, including those lovely perchlorates we discussed, so it needs extensive purification before it's safe for drinking or agriculture. Even after extraction and purification, water remains your most precious resource. Every drop must be recycled with extreme efficiency. On the International Space Station, advanced water recycling systems recover about 93 to 94% of water from all sources: humidity in the air, urine, sweat, even expelled breath. The remaining 6 to 7% is lost and must be resupplied. A Mars colony needs even higher efficiency because resupply is so difficult and expensive. You need systems approaching 98 or 99% water recovery. Any loss represents an ongoing drain on your water reserves that must eventually be replenished by extracting and processing more Martian ice. These recycling systems are complex, with multiple failure points. They require regular maintenance, occasional replacement parts, and careful monitoring. They can break down. When your water recycler malfunctions and your reserve tanks are running low, every repair attempt becomes a race against dehydration. And you need water for everything: drinking, cooking, growing food, hygiene, equipment cooling, chemical processes, producing oxygen through electrolysis. The total water requirements are substantial, and managing the supply chain, extraction, purification, distribution, use, recovery, recycling, becomes one of the mission's central challenges. Now let's zoom out and contemplate the sheer isolation in terms of resources and problem solving. On Earth, even in remote locations, you're part of a global civilization. If you need a specialized piece of equipment, you can order it. If you have a technical problem you can't solve, you can consult experts. If something breaks, you can often get replacement parts shipped relatively quickly. Manufacturing and supply chains span the planet, providing redundancy and accessibility. On Mars, you have what you brought with you and nothing more except what arrives during pre-scheduled resupply missions years apart. If a critical component breaks and you don't have a spare, you need to either repair it with whatever materials and tools are available or improvise a workaround. MacGyver-style improvisation sounds exciting in movies, but in reality, it's terrifying when your life depends on successfully jury-rigging a solution to a problem you weren't trained for, using inadequate materials, under time pressure, without being able to consult with experts in real time. The Mars missions will carry 3D printers and feedstock materials specifically to manufacture replacement parts and tools. This sounds like a comprehensive solution until you examine the limitations. 3D printers can create objects from plastics, certain metals, and composite materials, but they can't manufacture everything. Electronic components, specialized sensors, complex mechanical assemblies, optical systems, many critical items can't be 3D printed with current technology. You'll have a substantial inventory of spare parts for critical systems, carefully selected based on failure probability and criticality analysis. But you can't bring spares for everything. The mass would be prohibitive. Mission planners make calculated bets about what might break and what can be repaired or improvised. Sometimes those bets will be wrong. Research on failure modes for long-duration space missions shows that unexpected failures are almost guaranteed. Complex systems interact in unpredictable ways. Components fail for unanticipated reasons. Environmental factors that seemed minor turn out to be significant. The history of space exploration is filled with examples of unexpected problems. Apollo 13's oxygen tank explosion, the near disaster when a Progress supply ship collided with Mir, the cooling system problems on the International Space Station. Each of these crises was resolved through a combination of engineering expertise, creative problem-solving, and often considerable luck. But they all occurred in low Earth orbit with the possibility of crew evacuation and relatively quick resupply. On Mars, you can't evacuate. You can't receive emergency supplies. You solve the problem with what you have, or you die. Let's talk about something that sounds simple but becomes a nightmare on Mars: communication with Earth. You're accustomed to instant communication. You send a message and within seconds you get a response. You have a question, you search online, you get answers immediately. You feel isolated, you call someone, you hear their voice in real time. This instant connectivity is so fundamental to modern life that we barely notice it until it's taken away. On Mars, the speed of light becomes your enemy. Radio signals travel at light speed, roughly 300,000 kilometers per second. That sounds fast until you're separated by the vast distance between Earth and Mars. At its closest approach, Mars is about 55 million kilometers from Earth. At its farthest, it's about 400 million kilometers away. The distance varies constantly as both planets orbit the Sun at different speeds. This means communication delay. The time between sending a message and receiving a response ranges from about 6 minutes at closest approach to 44 minutes at maximum distance. Most of the time, you're looking at delays of 10 to 20 minutes each way. Think about what that means for a conversation. You ask a question, 20 minutes pass, you receive an answer, you ask a follow-up question. Another 20 minutes pass. A simple back-and-forth exchange that would take 2 minutes on Earth stretches into nearly an hour. A complex technical discussion that would normally take 30 minutes becomes a multi-hour ordeal. Real-time conversation is impossible. You can't have a phone call with your family where you hear their voices responding to yours. You can't video chat with your children as they tell you about their day. Every communication becomes asynchronous. You record messages, send them, and wait for recorded responses. The natural flow of human conversation is broken. The psychological impact is profound. Research on isolated populations shows that communication with loved ones is crucial for maintaining mental health. Prisoners in solitary confinement, Antarctic researchers, submarine crews, all report that connection with family and friends helps them endure isolation and hardship. But even the most isolated people on Earth can have real-time phone conversations. You can't. Your daughter has her first day of school. By the time you see the video message your spouse sent, the day is long over. You can't ask how it went and hear the answer. You can send a message saying you're proud of her, but it won't arrive for 20 minutes, and her response won't come back for another 20. The moment has passed. You're not participating in her life, you're watching a delayed broadcast of it. A medical emergency occurs in your family, your parent is hospitalized. By the time you receive the message, hours have passed Earth time. You have no idea if they're stable, deteriorating, or if the crisis has already resolved. You can't talk to the doctors, you can't be there. All you can do is send messages of support into the void and wait, helpless and terrified, for updates that arrive in agonizing increments. Your relationship with your partner begins to strain under the distance and delay. Arguments that could be resolved with a 10-minute conversation instead stretch out over days, with each delayed response providing time for resentment and misunderstanding to fester. The emotional connection that sustains relationships requires presence and responsiveness, things that communication delay makes nearly impossible. Research published in January 2026 examined how communication delays affect team performance and psychological well-being in simulated Mars missions. The study found that as delay increased, participants reported feeling more isolated, frustrated, and disconnected from support networks on Earth. Decision-making became more difficult when expertise couldn't be consulted in real time. Team cohesion suffered when conflicts couldn't be resolved through immediate dialogue, and the communication infrastructure itself is fragile and limited. Mars communications rely on orbital relay satellites and direct transmission during times when Earth is above the Martian horizon. Sometimes the Sun passes directly between Earth and Mars, an event called solar conjunction that occurs approximately every 26 months and lasts about 2 to 3 weeks. During this period, the Sun's radiation disrupts radio communications, creating a communications blackout. For 2 to 3 weeks, you have minimal or no contact with Earth, no messages from family, no technical support, no mission updates. You're truly alone with just your crew, knowing that if something goes catastrophically wrong during this window, no one on Earth will even know until communications resume. The bandwidth available for Mars-Earth communications is also extremely limited compared to terrestrial internet. NASA's Mars Reconnaissance Orbiter, which has one of the highest data transmission rates of Mars missions, can send data to Earth at about 2 megabits per second under optimal conditions, roughly the speed of dial-up internet from the 1990s. And that bandwidth must be shared among scientific data, engineering telemetry, crew communications, and all other needs. This means you can't casually video call home whenever you want. Video messages must be compressed and scheduled. Your internet browsing is limited to cached content and carefully prioritized downloads. You can't watch new movies or shows streaming in real time. You can't follow social media. You can't participate in online communities. The digital connectivity that pervades modern life simply doesn't exist on Mars. You're cut off in a way that's difficult for anyone who's grown up with internet connectivity to truly comprehend. Now let's discuss what happens when things go wrong with critical systems, not just equipment failures, but design flaws or unforeseen interactions that create existential threats. Engineering complex life support systems for extreme environments is extraordinarily difficult. Despite extensive testing, simulations, and redundancy, unexpected problems emerge when systems operate under real-world conditions for extended periods. Consider the Biosphere 2 experiment conducted in the early 1990s. 8 people sealed themselves inside a large, closed ecological system in Arizona, attempting to create a self-sustaining environment with plants producing oxygen, waste being composted, water being recycled, essentially a test run for the kind of closed-loop life support that Mars would require. The experiment encountered serious problems. Oxygen levels dropped unexpectedly as soil microbes consumed more oxygen than anticipated. Carbon dioxide levels fluctuated wildly, requiring intervention to add oxygen from outside. Nitrous oxide reached dangerous levels. The food production system didn't yield as much as planned, and participants lost significant weight. Interpersonal conflicts divided the crew. The ecosystem became unbalanced, with some species thriving while others died off. And this was in a facility on Earth with normal gravity, protection from radiation, ability to bring in supplies if absolutely necessary, and immediate access to outside experts. It still nearly failed. A Mars habitat will be far more constrained, smaller, more dependent on technology, less biological diversity, no possibility of emergency resupply. The closed-loop systems must work nearly perfectly for years. Any imbalance that develops must be detected early and corrected with available resources, or it will cascade into life-threatening crisis. Let me give you a specific scenario: carbon dioxide scrubbing. Your habitat's atmosphere control system removes carbon dioxide that you exhale and either vents it or converts it into useful products. Various technologies exist for this: chemical scrubbers using lithium hydroxide or metal oxides, molecular sieves, mechanical separation systems. All require maintenance and periodic regeneration or replacement of consumables. What happens if your CO2 scrubbing system becomes less efficient over time due to degradation you didn't anticipate? Carbon dioxide levels begin to rise slowly, not rapidly enough to trigger alarms immediately, but gradually increasing over weeks. At normal Earth atmospheric levels, carbon dioxide is about 0.04%. At 1%, you experience slight drowsiness and decreased concentration, symptoms easily attributed to other factors like stress or poor sleep. At 2%, breathing deepens, headaches occur, cognitive performance degrades noticeably. At 3 to 4%, you experience severe headaches, dizziness, increased heart rate, difficulty breathing, and impaired judgment. Here's the insidious part. Impaired judgment means you're less capable of recognizing that something is wrong and responding appropriately. By the time symptoms are severe enough to be obviously problematic, your ability to think clearly and solve the problem is compromised. In a confined habitat where everyone is exposed to the same atmospheric contamination, the entire crew deteriorates simultaneously. There's no healthy person to recognize what's happening and intervene. Automated systems should detect rising CO2 levels, but what if the sensors have drifted out of calibration? What if the alarm systems malfunction? What if the crew, in their impaired state, dismisses warnings as false alarms? This isn't theoretical. In submarine accidents, carbon dioxide buildup has contributed to crew incapacitation. In spacecraft incidents, atmospheric contamination has created dangerous situations. The Apollo 13 mission dealt with rising CO2 levels after their primary scrubbing system was in the damaged service module, forcing them to improvise scrubbers using materials available in the command and lunar modules. On Mars, you don't have the option of aborting to Earth. If atmospheric systems fail and you can't repair them with available resources, you suffocate, slowly, painfully, while desperately trying to fix the problem with diminishing cognitive capacity. Let's talk about fire because it's one of the most terrifying scenarios imaginable in a sealed habitat. Fire in a spacecraft or habitat is catastrophically dangerous. You're in a confined space filled with oxygen that you need to breathe but that also feeds flames. Fire produces toxic smoke and combustion products that contaminate your atmosphere. The heat can damage critical systems. Fighting the fire consumes precious resources and risks crew injury. In the Apollo 1 tragedy of 1967, a cabin fire during a ground test killed 3 astronauts in seconds. The cabin was pressurized with pure oxygen at higher than atmospheric pressure, a decision made to simplify systems, but which created an environment where materials that are normally fire-resistant burned intensely. The crew had no time to escape. The fire burned through hatches and systems almost instantly. It was a horrific demonstration of how dangerous fire is in spacecraft environments. Modern spacecraft and habitat designs use air mixtures closer to Earth's atmosphere, about 21% oxygen, the rest nitrogen or other inert gases. This reduces fire risk but doesn't eliminate it. Materials are carefully selected to be fire-resistant. Fire suppression systems are installed, but the risk remains. On Mars, a fire in your habitat could destroy systems you can't replace. The smoke and combustion products contaminate your atmosphere, requiring extensive scrubbing to make the air breathable again. The fire consumes oxygen, and while you can generate more, your production rate is limited. If the fire is severe enough, you might need to evacuate sections of the habitat, reducing your living space and potentially cutting you off from critical systems or supplies. And fighting a fire in reduced gravity creates unique challenges. Fire behaves differently without strong convection currents. Flames don't rise the same way. Smoke doesn't clear by rising to the ceiling. Water droplets from fire suppression systems don't fall predictably. Your intuitions about how to fight fires, developed in Earth gravity, may lead you astray. A study published in Fire Technology examined fire behavior in reduced gravity environments. Researchers found that flames spread differently, materials burn in unexpected ways, and extinguishment techniques effective on Earth may be less effective in partial gravity. Fire suppression systems designed for Mars habitats need to account for these differences, but real-world testing in Martian gravity is obviously impossible before missions occur. Now let me tell you about something even more subtle and terrifying: the possibility of contamination with Martian materials that have unexpected biological or chemical effects. We don't know for certain whether Mars has ever harbored life or whether any microbial life might still exist in protected subsurface environments. This uncertainty creates a serious problem. Planetary protection protocols exist to prevent contamination in both directions. Earth microbes contaminating Mars and potentially interfering with scientific investigations, and Martian materials potentially contaminating Earth's biosphere. For sample return missions, extensive containment and sterilization protocols are planned. But for human missions, perfect containment is impossible. You'll be living on Mars, walking on the surface, bringing Martian dust into airlocks, and inevitably, despite best efforts, some amount into the habitat. You'll drill into the subsurface to extract water ice. You'll process Martian materials to extract resources. What if Martian soil contains organic compounds or minerals that have unexpected toxic effects with prolonged exposure? What if there are chemical reactions between Martian materials and habitat systems that create dangerous byproducts? What if, and this is a long shot but not impossible, there are Martian microorganisms that can survive in habitat conditions and interact with systems or crew in harmful ways? The probability of encountering dangerous Martian life is considered low by most astrobiologists, but it's not zero, and the consequences of being wrong could range from minor nuisance to catastrophic. Earth's immune system has evolved to handle Earth pathogens. An alien biochemistry, even if microbial and simple, might interact with human biology in completely unexpected ways. This concern isn't pure science fiction. When Apollo astronauts returned from the Moon with lunar samples, they were quarantined until scientists could verify the Moon was biologically sterile. The quarantine procedures turned out to be unnecessary. The Moon is lifeless, but the precaution reflected legitimate concern about unknown risks. Mars is more likely to have life or have had life than the Moon. The planet had liquid water, potentially habitable environments, and complex chemistry. We've found organic molecules in Martian samples. We've detected methane in the atmosphere that might have biological sources, though geological sources are also possible. You'll be living in this uncertainty. Every time you come in from surface activities, you'll follow decontamination procedures, but you'll know that perfection is impossible. Some amount of Martian material is entering your living space. Probably it's harmless, almost certainly it's harmless, but almost certainly isn't the same as certainly, and you'll live with that small, nagging doubt. Check out this other video on the screen. Why the first humans on Mars will never come back. It goes even deeper into the one-way aspects of this journey and explores why some scientists believe the first Mars colonists might not have a choice about returning. I am sure you will love it. See you there.